The initial aim of this project was to control an off-the-shelf robotic arm using either a Kinect or a leap motion. The project has since evolved, requiring the use of both the Kinect and the leap. Another addition is the incorporation of a moving assembly, which is also controlled remotely. Having the robotic arm attached to a moving assembly increases the range at which it can operate, as well as making it generally more useful. For example, one could direct it to the end of a room to pick a coffee mug and then return it back to the user. In terms of motion capture, the project can be divided into two largely independent components: control of the robotic arm and control of the moving assembly. We will begin by providing a brief overview of the architecture required in order to control the robotic arm. The arm consists of 6 servos, 5 powering the various joints and 1 powering the gripper at the end of the arm. For control, we will attempt to map the configuration of each human arm joint to the servo joints. We will do this through markerless motion capture of the user's right arm. The Kinect is an obvious candidate for this, since it provides a skeleton API which tracks several joints in the human body, including those present in the arms. By knowing the location of 3 adjacent joints in 3-dimensional space, the angle between them can be determined using some trigonometric computations. The angle will have a direct mapping to the corresponding servo position. Unfortunately, the Kinect is not precise enough to track the finer movements of the human wrist and hand. As such, we will be required to use a different technique. For this purpose, we will use a leap motion, which was specially designed to track such movements. One important point to make is that the leap motion has a limited operating range, being able to track only between a range from 25 up to 600 millimeters. In order to increase the range of movements a user can perform, a structure has been devised that aims to keep the leap motion within operating range at all times, irrespective of the position of the human arm. The structure is attached to the base of the forearm, being impervious to forearm rotation movements. Through these two devices, joint parameters are computed on the computer, which are then converted to a serial UART TDL signal, which is sent via radio to the microcontroller operating the robotic arm. The second component we will look at is the moving assembly. Locomotion is controlled through a custom-designed inertial motion capture glove that consists of an accelerometer gyroscope sensor, a microcontroller, and an XB transceiver which relays the data. The components on the glove are powered by 4 AAA batteries with a power switch that closes and opens the circuit. Communication is done through the XB protocol. On the receiving end, we have the robot intercepting the data sent from the UART TDL RF interface, as well as data coming from the glove through the XB protocol. The robot structure is an inverse T-shaped structure, providing a good surface area for attaching the robotic arm, as well as great balance, thanks to the wide surface area of its base. The structure is made out of wood, its weight being an additional advantage, aiding considerably in balance, thanks to inertia. In order to make the robot mobile, a power system has been devised, consisting of several high-capacity batteries, providing a total of 15 volts. As each subsystem requires a different voltage, a set of 3 voltage regulators is present, providing 12 volts, 9 volts, and 5 volts respectively. As with the glove, a power switch is present, which opens and closes the circuit. The robotic arm is attached to the side of the structure, having its own radio module, thus allowing it to intercept commands. An AVR program written for the microcontroller that operates the arm sets the servos to their required position. The structure is placed on 2 Rover 5 chassis, which provides movement. The rovers are controlled through the means of a motor driver board, which converts pulse width modulation and direction signals into an analog voltage between -9 and 9 volts. The pulse width modulation and direction signals are sent by an Arduino, which sets the signals according to the orientation data received from the glove through the XB protocol. In order to control the robot from a distance, telemetry and visual audio feeds need to be passed back to the controller. For the purpose of this project, the data is recorded by an iPhone 5S, which relays data back using the IP networking model inside an intranet to which both the iPhone and the computer are connected to. A piece of software running on the computer displays data acquired from both the Kinect and the Leap, as well as a video feed acquired over HTTP from the iPhone 5S. The software also allows manual control of the robotic arm through the use of several sliders. Lastly, we'll showcase some of the functionality. We will first begin by looking at how the robotic arm can be controlled, first through the means of the Kinect. In this video, the Kinect is used to operate the shoulder joint, providing translation and rotation. For the second example, we'll demonstrate the use of the Leap on top of the structure. As can be seen, the Leap maintains its relative position, irrespective of the movement of the arm. In this video, rotation of the wrist is monitored, as well as the opening of the hand, allowing the user to open and close the gripper. Finally, we will showcase how locomotion can be controlled through the means of the inertial glove. Note that the robot has been fitted with a speaker and an audio module, allowing it to make various sounds. Commands can be described as follows. A hand pointing down equates to a forward motion. A hand pointing upwards equates to a backwards motion. And a hand pointing sideways equates to lateral left or right in place rotation. This concludes our presentation. Thank you for watching. Bye-bye.